2 minutes before the world's most powerful telescopes locked onto it again, something happened to the strange visitor from beyond our solar system that no comet in recorded human history had ever done. A tightly focused beam of glowing material shot outward from the nucleus of 3IATLAS, and instead of streaming away from the sun the way every single cometary tail ever observed by astronomers has behaved for as long as telescopes have existed, this beam pointed directly at it, straight toward our star, defying more than 4 centuries of settled cometary physics in a single startling image. And the scientists who first noticed it on Hubble Space Telescope data could not immediately explain what they were looking at, because everything we know about how comets work says this should not be possible. Comets develop tails because sunlight and the solar wind physically push dust and gas away from the nucleus. Radiation pressure and charged particles streaming off the sun act like a cosmic hairdryer, blowing loose material backward into the long, glowing tails that have inspired human wonder and fear for thousands of years. So a jet of material, pointed the opposite direction, straight back toward the very source of the pressure that is supposed to be blowing it away, is not a small anomaly. It is a direct contradiction of basic physics, as astronomers have understood it since the days when comets were first correctly explained as icy bodies venting gas as they approach the sun, and yet there it was in the data, first spotted in Hubble imagery captured on July 21st, 2025, showing a glowing halo around the object that extended noticeably further on the sunward side than anywhere else, an asymmetry that at first glance might have been dismissed as a processing artifact or an observational quirk. Except that as more images arrived from more instruments over the following months, the pattern only became clearer and stranger, revealing what astronomers now call an anti-tail, a jet of material extending outward from the nucleus of 3IATLAS toward the sun, rather than away from it, visible not just in one image from one telescope, but repeatedly, consistently, and increasingly dramatically, as the object made its historic journey through our solar system. To understand why this matters so much, you first need to understand what 3IATLAS actually is, because this is not some ordinary comet that wandered too close to the sun. It is only the third interstellar object ever confirmed to pass through our solar system. An object that originated not from our own sun's distant cloud of icy debris, but from somewhere else entirely. Another star system, flung across the vast emptiness of interstellar space, for what researchers estimate could be anywhere from 3 to 11 billion years before, finally, almost impossibly, passing close enough to our own sun for our telescopes to catch it, discovered on July 1st, 2025, by the aptly named Asteroid Terrestrial Impact Last Alert System, the survey telescope network in Chile designed primarily to watch for asteroids that might threaten Earth. And almost immediately after discovery, astronomers realized this object was not behaving like anything that belonged to our solar system. Its trajectory was far too fast, far too straight, and far too extreme to have been captured by our sun's gravity the way ordinary comets and asteroids are. Instead, it was moving on what astronomers call a hyperbolic trajectory, meaning it was never gravitationally bound to our sun at all. It simply came screaming in from interstellar space at more than 130,000 miles per hour, swung around our star in a single dramatic pass, and is now on its way back out into the emptiness between the stars, never to return, joining an extremely short list of confirmed interstellar visitors that includes only 2 previous objects: the cigar-shaped Oumuamua, discovered in 2017, and the comet Borisov, discovered in 2019, both of which came and went relatively quietly by comparison. But 3IATLAS is different, both in scale and in strangeness, with Hubble Space Telescope observations suggesting its icy nucleus measures somewhere between 440 meters and as much as 5.5 kilometers across, making it potentially far larger than either of the 2 interstellar objects that came before it, and its behavior as it approached the sun turned out to be stranger still. As 3IATLAS drew closer to our star throughout the second half of 2025, it began doing exactly what scientists expected a comet to do, developing a coma, the fuzzy glowing envelope of gas and dust that forms around a comet's icy nucleus as solar heating causes its surface ices to sublimate directly from solid to gas, and then developing what appeared to be a normal cometary tail, streaming away from the sun as radiation pressure pushed the liberated material backward. All standard, all expected. All consistent with what more than a century of cometary science predicts. But layered on top of that ordinary behavior was something that was not ordinary at all. The persistent glowing anti-tail pointed directly sunward, and as astronomers using ground-based observatories like the 2-meter twin telescope in Tenerife, Spain, along with repeated follow-up observations from Hubble itself, continued tracking the object through its closest approach to the sun on October 29, 2025, and beyond, The sunward jet did not fade or disappear the way a simple optical illusion or imaging artifact would have. Instead, it grew more prominent, more structured, and considerably more difficult to explain with any simple, conventional model, with researchers eventually measuring the jet extending outward from the nucleus by as much as 400,000 kilometers, a distance greater than the gap between the Earth and the Moon. All of it pointed squarely at the sun rather than away from it. And further analysis revealed the jet was not just present but tightly collimated, meaning it stayed remarkably narrow and focused rather than spreading out into a diffuse cloud the way you would expect gas and dust to behave once released into the vacuum of space, with some measurements showing the beam staying within roughly 8 degrees of a consistent central axis out to distances of 500,000 kilometers from the nucleus, a level of precision and stability that one prominent researcher described as behaving almost like the beam of a lighthouse, sweeping around with the object's rotation rather than dispersing randomly the way sea material typically would. The leading scientific explanation, and the one embraced by the overwhelming majority of astronomers studying 3IATLAS, including researchers at NASA, is rooted firmly in ordinary, if unusually intense, cometary physics. The theory holds that as the sun-facing side of the nucleus heated up during the object's approach to perihelion, it experienced dramatically enhanced mass loss compared to the shadowed side, essentially boiling off far more ice and dust from the side facing the sun than from the side facing away. And observations using NASA's SphereX infrared observatory added an important piece to this puzzle, revealing a near total absence of the very fine sub-micron dust particles that solar radiation pressure most easily pushes around. With the dust grains detected around 3IATLAS instead measuring roughly 1/10 of a millimeter in radius, particles heavy enough that they simply are not swept backward by sunlight and solar wind pressure with anywhere near the same efficiency as the fine dust found in typical solar system comets. And without that pressure reliably clearing material away from the sunward side, the theory goes, larger fragments and grains ejected from the sun. Facing hemisphere could linger in place long enough to scatter sunlight and produce exactly the glowing, sunward-pointing structure that telescopes have been recording. A related explanation focuses specifically on ice rather than dust, suggesting that tiny fragments of water ice shed from the sun-facing surface evaporate so quickly in the heat of direct sunlight that they simply do not survive long enough for radiation pressure to meaningfully push them backward before they turn to gas and vanish, meaning what we are actually seeing in the images is the brief, glowing scattering of sunlight off ice particles in the fleeting moment between their release and their evaporation, a process that would naturally appear to hang in the sunward direction precisely because that is where the heating, and therefore the ice loss, is most intense. And both of these explanations are reinforced by additional data showing a dramatic shift in the object's composition as it passed through perihelion, with the strong water ice absorption features present in pre-perihelion spectra from August 2025, having essentially vanished by the time researchers examined post-perihelion data, replaced instead by a spectral signature dominated by thermal emission and sunlight scattered off what scientists describe as organosilicaceous dust grains, material rich in both organic compounds and silicate minerals, suggesting the intense heating 3IATLAS experienced near the sun fundamentally altered the character of the material being ejected from its surface, consistent with a genuinely unusual but still entirely natural comet undergoing an especially dramatic and asymmetric bout of solar heating. But not every researcher studying this object has been satisfied that ordinary cometary physics fully explains everything observed. And the most vocal and widely quoted dissenting voice belongs to Avi Loeb, the Harvard astronomer whose name has become closely associated with the search for possible technological signatures among unusual celestial objects ever since he controversially suggested the very first interstellar object, Oumuamua, might have been artificial back in 2017. And Loeb has approached 3IATLAS with the same instinct, cataloging what he describes as a growing list of anomalies surrounding the object, pointing specifically to the improbable statistics behind the sunward jet's persistence and precision, noting in his published analysis that the odds of a tightly collimated anti-tail jet appearing consistently in the sunward direction both before and after the object's closest approach to the sun, purely by chance alignment of the nucleus's rotation axis, work out to something in the range of 25 in 100,000, and further observing that the jet's tight collimation, staying within roughly 8 degrees of its axis, out to enormous distances from the nucleus, is itself a second independently unlikely occurrence. And Loeb has gone further still, highlighting later Hubble observations from November and December 2025 that revealed not just the single dominant anti-tail, but what he describes as 3 separate evolving jets emerging from the object at what appear to be regular angular intervals from one another, structure that he argues is difficult to reconcile with the kind of random, chaotic outgassing typically seen on natural cometary surfaces, and it is against this backdrop of statistical improbability that Loeb has openly floated, among a long list of other possible explanations he says should remain on the table, the far more speculative idea that the sunward beam could theoretically represent something engineered, even suggesting in one of his public essays that if 3IATLAS were artificial, a directed sunward jet might serve a defensive function, something akin to a beam designed to help the object mitigate the risk of impacts from micrometeorites or small rocks as it plows through the inner solar system at extraordinary speed. A genuinely provocative idea that has attracted enormous public attention and media coverage throughout the interstellar object's journey through our solar system. But it is important. To be clear about where the broader scientific community actually stands on this question, because Loeb's alien technology hypothesis, however headline-grabbing, remains very much a minority position, and it has been directly and repeatedly challenged by other working astronomers, including Jason Wright of Pennsylvania State University, who has pointed to previous documented cases of similar sunward brightening enhancements around ordinary solar system comets caused by exactly the kind of large, heavy dust grains that fail to get swept backward by solar wind pressure, arguing that what we are seeing around 3IATLAS, while unusually pronounced, fits within a known, if uncommon, category of natural cometary behavior, rather than requiring anything exotic to explain it. And researchers at the European Space Agency have similarly, its time in our solar system having entered on a trajectory so extreme that it was never gravitationally captured by our sun, even briefly, sweeping around perihelion at a closest solar distance of about 1.4 astronomical units, just inside the orbit of Mars, before beginning its long final journey back out into the depths of interstellar space at the same blistering speed it arrived with, never to return to our solar system again. And it is precisely this fleeting, one-time nature of the encounter that has made every single observation of 3IATLAS, including that strange, persistent, physics-defying beam pointed straight at the sun, so scientifically precious, because unlike comets, native to our own solar system that swing past the sun on predictable orbits every few years or decades, giving astronomers repeated opportunities to study and refine their understanding, 3IATLAS offered exactly one chance, one narrow window of a few months, to observe an object that had been traveling through the emptiness between the stars for potentially billions of years before, finally, almost accidentally, wandering close enough to our own star for humanity's most advanced instruments to catch a glimpse before it vanished again forever, carrying with it whatever the true explanation for that strange sunward beam actually is out into the interstellar darkness, quite possibly never to be resolved with total certainty, leaving astronomers with a genuinely rare scientific puzzle, one grounded overwhelmingly in extreme, asymmetric, and still not fully understood natural cometary physics, but tantalizing enough in its statistical improbability and its structural precision that even now, months after the object made its closest approach to the sun and began its irreversible journey back out into the void, researchers are still combing through the data, still arguing over competing explanations, and still, in at least one prominent case, refusing to entirely rule out the far stranger possibility that what we witnessed streaming toward our sun was not simply an unusually intense burst of natural outgassing, but something that defied not just 4 centuries of cometary science, but our entire understanding of what belongs and what does not belong, drifting silently through the emptiness of interstellar space. And to really appreciate just how strange this whole episode has been for the professional astronomy community, it helps to rewind to the very first hours after discovery, back to July 1st, 2025, when a routine overnight scan by the ATLAS survey system in Rio Hurtado, Chile, a network of telescopes built and funded specifically to catch asteroids on a potential collision course with Earth before it is too late to react, picked up a faint moving point of light that did not match anything in the catalog of known solar system objects, and within a single day, the International Astronomical Union's Minor Planet Center, JOI, decrunched the preliminary orbital numbers and announced something that sends a ripple of excitement through every professional astronomer's inbox, maybe once every several years, that this object, briefly designated A11PL3Z before receiving its permanent name, was not bound to our sun at all. Its orbital eccentricity, the mathematical measure of how stretched out and open an orbit is, came out to roughly 6.14, a number so far beyond the value of 1.0. That marks the boundary between a closed elliptical orbit and an open one-way hyperbolic path. That there was no ambiguity whatsoever. This thing came from somewhere else, and it was going somewhere else. and our solar system was merely a brief, one-time waypoint on a journey that began around another star entirely, and researchers, scrambling to characterize the newly confirmed interstellar object, quickly discovered something else remarkable buried in old archival data. Because telescopes around the world routinely photograph huge swaths of sky as part of ongoing survey programs. And once astronomers know where and when to look, they can often find an object hiding in images taken before its official discovery. And sure enough, pre-discovery images of 3IATLAS turned up stretching back weeks before the July 1st announcement, giving scientists an even longer baseline of data to refine its trajectory and confirm just how extreme and unusual its path through the solar system truly was, a path that researchers determined was oriented almost perpendicular to the Sun's own motion through the Milky Way, arriving from the general direction of the constellation Sagittarius, which, not coincidentally, happens to be the direction of the crowded, star-dense center of our own galaxy, a detail that led some researchers studying the object's likely origin to propose that 3I-ATLAS most probably formed and spent most of its multi-billion-year existence drifting through what astronomers call the galaxy's thick disk, an ancient, puffed-up population of older stars that together make up roughly 2/3 of all the stars in the Milky Way. Though, as one astronomer involved in that research was quick to caution, pinning down precisely which star or region of the galaxy 3I-ATLAS actually originated from remains essentially impossible with current data, the object could realistically have been ejected from the gravitational neighborhood of any number of ancient stars long before our own sun had even finished forming, making its exact birthplace one mystery that may simply never be solved. What makes the sunward beam discovery even more remarkable is the sheer scale of the international observation campaign that documented it, because unlike the two interstellar objects discovered before it, both of which were spotted relatively late in their solar system passages and observed with comparatively modest resources, 3I-ATLAS was caught early enough and recognized as significant enough that essentially every major space telescope and observatory capable of studying it was pointed in its direction. At some point during its journey, the Hubble Space Telescope captured multiple rounds of high-resolution imaging throughout the second half of 2025 and into early 2026. Each new observation adding another data point to the growing anti-tail mystery. The James Webb Space Telescope brought its powerful infrared instruments to bear, probing the chemical composition of the gas and dust surrounding the nucleus in ways that optical telescopes simply cannot match. NASA's Parker Solar Probe, a spacecraft built and shielded specifically to survive extreme proximity to the Sun, found itself in an unexpectedly useful position to observe the interstellar visitor from a genuinely unique vantage point unavailable to any Earth-based or Earth-orbiting instrument. The veteran SOHO Solar Observatory, which has spent decades staring continuously at the Sun to watch for solar flares and coronal mass ejections, caught its own glimpse of the object as it swept through the instrument's field of view near perihelion, and even spacecraft not designed with comets in mind got pulled into the effort, with the European Space Agency redirecting the cameras aboard both the ExoMars Trace Gas Orbiter and Mars Express toward 3I-ATLAS as it made its closest approach to any planet during its entire solar system passage, sweeping past Mars at a distance of roughly 18 million miles on October 3rd, 2025, close enough that the Trace Gas Orbiter's CAS's imaging instrument was able to capture a genuine, if admittedly fuzzy, series of direct images showing the interstellar object as a soft white dot moving steadily against the streaked backdrop of distant stars. Images that, when stitched together into a short animation, gave scientists and the public alike a rare, tangible glimpse of an object that had spent billions of years traveling through the emptiness between star systems before this brief and final encounter with our own. And beyond the traditional optical and infrared observatories, the sheer scientific importance of an interstellar visitor prompted an unusual mobilization of radio astronomy resources as well, with several of the world's most sensitive radio telescopes, including the Allen Telescope Array, the Meerkat Array in South Africa, the Green Bank Telescope in the United States, and China's enormous Fast Radio Telescope, all independently conducting dedicated searches for what scientists call technosignatures, narrowband or periodic radio signals that would indicate artificial origin. A search motivated in part by the long-running scientific curiosity about whether any interstellar object passing through our solar system might, however unlikely, carry some trace of technological origin. And it is worth being completely clear and honest about what those searches found, because across every single one of these dedicated radio surveys, using some of the most sensitive listening equipment ever built by humanity, not one credible, repeatable artificial signal was ever detected coming from 3I-ATLAS, a total absence of evidence that stands as one of the strongest pieces of data supporting the natural comet explanation. even as the strange visual anomaly of that sunward pointing beam of light continued to defy simple, complete explanation using conventional models alone. As the months went on and more data rolled in from telescope after telescope, the picture of 3IATLAS that emerged was one of genuine scientific richness layered on top of persistent mystery. Astronomers tracking its rotation determined that the object's spin axis remained pointed toward the sun to within just 7 or 8 degrees for an extended period both before and after its closest approach, an alignment so precise that by pure chance alone, it would be expected to occur only a small fraction of the time. And it was this precise alignment researchers eventually realized that explained why the sunward jet appeared so remarkably stable and tightly focused, rather than sweeping widely across the sky the way you might expect from a jet erupting off a tumbling, randomly oriented nucleus. Because if the rotation axis truly was locked in close alignment with the sunward direction, then whichever hemisphere of the nucleus happened to be facing the sun at any given rotation would consistently be the hemisphere producing the strongest outgassing, effectively pinning the resulting jet in a stable sunward orientation, regardless of how quickly the nucleus itself was spinning underneath it. And this discovery led directly to an even stranger follow-up puzzle that Avi Loeb and his collaborators highlighted in later analysis, because the anti-tail jet did not simply vanish once 3IATLAS swept past perihelion, and the hemisphere that had been facing the sun rotated into shadow. Instead, observations continued to show a persistent sunward jet even after perihelion, which meant that an entirely different hemisphere of the nucleus, one that had spent the entire approach phase in shadow on the object's night side, had apparently developed its own capacity for intense sunward outgassing almost as soon as it rotated into direct sunlight, implying, if the natural comet explanation is correct, the presence of a second concentrated pocket of volatile ice positioned near the opposite pole of the rotation axis from the first, a scenario researchers acknowledge is not impossible for a genuinely ancient, chemically complex comet nucleus, but one that does require a fairly specific and somewhat fortunate geological history to produce 2 independently active polar regions capable of generating such precisely aligned jets. And it is exactly this kind of stacking anomaly upon anomaly, the improbable rotational alignment, the improbable jet collimation, and now the improbable existence of matching active regions on opposite poles of the nucleus that has kept the scientific conversation around 3IATLAS unusually lively and unresolved, even as the object itself recedes further and further from the sun on its one-way journey back into interstellar space, never to be observed by human instruments again, leaving behind a dataset that astronomers will likely spend years, if not decades, continuing to analyze, debate, and attempt to fully explain.